Two of the biggest problems facing the technology industry are big data and optimization. The problem of big data arises because everything that is done with technology produces data. As people allow more technology into their lives, the amount of data produced each year increases enormously. Computers are now unable to keep up with the amount of data that we produce. Optimization problems are finding the best solution from all feasible solutions. The reason that existing computers are so bad at solving optimization problems is because when you ask an existing computer to solve such a problem, it is like asking someone to find the lowest point in an area of land. In essence, an existing computer solves the problem by sending out one person to walk across all the land and find the lowest point and then report back. This can take huge amounts of time. The core reason that existing computers have issues with optimization and big data is due to their architecture being bits, which can be a 0 or a 1. Because of this architecture, as you add more bits onto the computer, the amount of different arrangements of zeros and ones increases at a rate of 2 to the power of n being the number of bits. The problem with this is that an existing computer can only be in one of the 2 to the n arrangements at once. This means that a computer can only work on one solution at a time. The technology sector needs a new way to combat the issues of big data and optimization. I, along with Google, Microsoft, and NASA, believe that quantum computing can be the solution by combining the quantum physics with computer science. Today, I will briefly explain what quantum physics is and discuss how two of the principles could be harnessed to build a quantum computer. I will then outline how a quantum computer could revolutionize a key sector of the New Zealand economy. So first, what is quantum mechanics, and what makes it different from classical physics? Classical physics governs the world we experience every day. For example, why an apple falls from a tree. In classical physics, it is possible to know both the position as well as the velocity of an object. Quantum mechanics governs a much stranger area of physics. In quantum mechanics, the more accurately the position of an object is known, the less accurately velocity is known about it, and vice versa. The first principle that I will explain today was made famous in the 1935 analogy by Erwin Schrodinger. In this analogy, Schrodinger's cat is placed in a box with a vial of poison gas. The vial has a random chance of breaking, killing the cat. When the lid is on the box, we do not know the state of the cat. The cat could be dead or alive. When something is in multiple states at the same time, it is called superposition. Under superposition, when the lid is on the box, the cat is both dead and alive at the same time. It is only by opening the box, observing the cat, and breaking the superposition that we discover if the cat is dead or alive. The analogy of Schrodinger's cat highlights the two key facts about superposition. When a system is not being observed, it is in all possible states at once, and that when a system is observed, the superposition collapses. Entanglement is the second principle of quantum mechanics that I will explain. It is also one of the weirdest. When it was first proposed in the 1930s, Einstein called it spooky action at a distance. The easiest way to think about entanglement is to imagine two spinners, each half red and half blue. If you entangled these spinners and spun them, then if the first spinner lands on blue, the second spinner must land on red. It does not matter how far apart the two spinners are. Both the principles of superposition and entanglement are being used to build quantum computers. Existing computers contain transistors that can be in the on or off position. This is the base architecture of all computers, namely zeros and ones, which are called bits. If you apply superposition to a bit, you get a qubit. A qubit can be both a 0 and a 1. One might conclude that only superposition is needed to provide the massive power of quantum computing. However, closer examination will show that an entanglement is an essential feature rather than just superposition itself. What entanglement does is create correlations between the qubits in a quantum processor. In this way, entanglement may be viewed as a special kind of superposition, where the entangled states are a superposition of the superposition. This means that while n number of bits can represent one arrangement of zeros and ones, n number of qubits can represent 2 to the n different arrangements at once. This means that while an existing computer can work on one solution at a time, a quantum computer can work on 2 to the n different things at the same time. The traveling salesman problem highlights the optimization ability of a quantum computer. In this problem, a traveling salesman is given a list of cities that he must visit and the distances between each of them. He's asked to visit each city once and then return to the original city in the shortest possible distance. While this seems like a simple problem, the number of cities grows at an exponential rate. For example, with 14 cities, there are 10 to the power of 11 routes. On NIWA's supercomputer that can undertake 65 trillion operations per second, it would take less than a second to solve this problem. If, however, there are 28 cities, it would take NIWA's supercomputer nearly 5,000 years to solve this problem. And with just 35 cities, it would take NIWA's supercomputer 14 billion years to solve this problem. NIWA's supercomputer is made of nearly 4,000 processors, which are trillions of classical bits. By comparison, with just 30 qubits, these same speeds could be achieved. And by adding just a few more qubits, 35 cities would take 100 seconds to solve, leaving existing supercomputers in the dust. Quantum computing's amazing computational power and the ability to solve optimization problems will be incredibly useful in a huge range of areas. Today, though, I'm going to focus on how quantum computers will revolutionize the primary industries, the core of the New Zealand economy. A major problem for these industries is that they are heavily reliant on the weather, and much of their decision-making is based around the likely impact of future weather conditions. To help with this, NIWA launched FarmMet, which is one of the most advanced weather forecasting systems in the world. The accuracy of a forecast can be judged in 4 key areas: parameterization, grid size, time step, and ensemble. The Earth's weather is the result of interactions between the Earth, atmosphere, and sea. In order to forecast the weather, FarmMet creates models which are a mathematical representation of the variables of the weather. Parameterization groups these variables together and simplifies them. Due to parameterization, instead of modeling exactly what each individual cloud will do, it instead gives a general idea of what all the clouds will do. When FarmMet creates a weather model, it divides the land, atmosphere, and sea into a horizontal grid at multiple altitudes. The smaller the size of each square in the grid, the higher the accuracy of the forecast. The time step is how often the variables are predicted in each square of the grid. Existing weather forecasts are also limited by unknowns or errors in their initial states. This can then cause larger errors in the predictions as the forecast moves further into the future. To minimize these errors, models are run multiple times with slightly different initial conditions, resulting in a collection of forecasts called an ensemble. Today, most global weather models have an ensemble of 30 to 50 forecasts. Weather forecasting is limited by how supercomputers can handle the problem of big data. FarmMet's forecasts are broken up into 3 different types: high accuracy forecast, a medium accuracy forecast, and a seasonal climate outlook. Each of these forecasts increases the amount of parameterization, the grid size, and the time step, and therefore the forecasts become less accurate and more generalized. On FarmMet's website, it states that the outlook doesn't tell you exactly what the weather will be on a day-to-day basis for the next 3 months. It is not possible to forecast that far out. Quantum computing will make the impossible possible. With the speed that a quantum computer can analyze big data, a forecast that has very little parameterization, a short time step, and a grid size that is just a few kilometers in area could be created far into the future. With the massive speed increase and parallel processing that quantum computers bring to the table, weather models could potentially be run with much larger ensembles, maybe even extending into the hundreds of thousands, further minimizing the negative effects of initial unknowns and errors. The resulting forecast from a quantum computer will allow people making decisions in the primary industries to be fully informed about the weather when they're making big decisions such as when to pick their crops. Many of the questions that farmers and orchardists ask are optimization questions. When is the best time to plant my crops? When is the best time to move my stock? The answer to these questions is dependent on the weather. Not only will a quantum computer be able to create super accurate long-term weather forecasts, but it'll also be able to use its optimization abilities to answer the questions asked by people working in the primary industries. This is something that has never been possible before. Humanity's understanding of mechanics powered the Industrial Revolution. The very basics of quantum mechanics allowed us to build semiconductors and lasers, which powered the technological revolution. Quantum computers are coming, and when they arrive, they will change the way in which humanity lives and works. New Zealand has a chance to become a world leader in quantum technology. With quantum computing, we can build a better future and a better New Zealand. Thank you.
Thank you, Jack. New Zealand's going to be a world leader in quantum computing ahead of Google.
So there's two options that New Zealand can take in this regard. The first is to invest in ourselves in trying to build the first quantum computer, which would be a very expensive project. We may want to do that with another country and maybe in partnership like with Australia. But there'd be lots of benefits from this. Any investment into science, technology, engineering, mathematics will help the industry as a whole, not just quantum physics. And then the second option is to allow someone else to build the first quantum computer, but to have processors and programmers in place so that when one is made, New Zealand can capitalize on it immediately and not just improve our primary industries, but also the many other applications of quantum computing.
How close is anybody to developing a quantum computer?
So at their Tech Ed conference in Auckland that was just last month, Microsoft came out and said that they believe they are 10 to 15 years away from building a quantum computer.
Is the weather really that predictable?
So the weather is pretty predictable because it all is just about getting the variables and then looking at what they've done and then looking at what they could possibly be doing in the future. And we
could possibly?
Yes. So it's all about probabilities. So if we look at what it has done in the past and we say, in the past, this has resulted in this, we can then look in the future and say that this is what it will probably do. And because of the speed that we will, with a quantum computer that will be able to analyze it, not just the past we'll be able to analyze better, but the future, we'll be able to build a much more accurate models than we do now.
That would be good news for climate science, wouldn't it?
Yeah, so the other thing that I was previously talking about before, due to time restrictions, I had to cut it out. I was going to talk about how you could, using a long-term climate model, so currently they also have climate models as well as weather forecasting, which really increase the parameterization and such. But, and they look at sort of the next 100 years. Well, using a quantum computer in that would be amazing, have much better long-term climate models. And then using the optimization abilities of a quantum computer, we could then say to a computer, how do we solve climate change? Because if we put in not only the weather variables, but also like CO2 emissions from cars and factories and all the different things, and also the cost of doing different things, it would be able to find the best way not only to reduce emissions, but also to do it the cheapest way possible.
So you're suggesting that quantum computing would take the guesswork out of everything?
Yes, eventually it would really destroy the probabilities around a lot of things because you're
able to... There goes the gambling industry then.
Yes, pretty much.
Good.
Which is probably a good thing, yeah. But the quantum computing is like most scientific, it's like the existing computers we have. They're a tool that we use, they're not only a great discovery within themselves, but the discoveries that it's led to. So with quantum computing, scientific analysis can just be done so much faster because a lot of science relies on using computers to do modeling and different things. So having that extra processing there will be massive for them. And then also in areas like health, where we need, which was another thing I was going to talk about, where we were going to, I was going to talk about predicting health outbreaks like Ebola before they happen, so that you can actually get resources in place before those things happen, and then also things like disease analysis and finding cures faster, because you just have that so much more processing.
Lucky I gave you a chance to put all that in there.
Yeah.
Thank you, Jack.